friends, this video on Oscillations part 19 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 18 before going ahead with part 19. Now let us talk about the total energy in SHM. Till now we talked about kinetic energy and potential energy individually. Let us talk about the total energy. So what would be the total energy in a simple harmonic motion? Total energy will be equal to kinetic energy plus potential energy. We generally represent total energy by E, kinetic energy plus potential energy. Now, what is the value of kinetic energy that we obtained in our previous slides? It is half k a squared sine squared omega t plus phi. And what is the value of potential energy? It is half k a squared cos squared omega t plus phi. Now if you take half k a squared common, so what do you get? It is sine squared omega t plus phi plus cos squared omega t plus phi. Now we know that sine squared theta plus cos squared theta is equal to 1. So this is of this form. So we can say that half k a squared, because this sine squared theta plus cos squared theta becomes equal to 1. So the value of total energy is equal to half k a squared. What does this show? This shows that total energy in case of a simple harmonic motion is a constant value, right? Because what is K? K is the force constant, which is equal to m omega squared, and A is the amplitude. So these three quantities are constant for a particular simple harmonic motion, right? So a particular simple harmonic motion will have a fixed value of amplitude, a fixed value of the mass, as well as a fixed value of the angular frequency. So the total energy is constant. It is not dependent on time. So the conclusion is total mechanical energy of a harmonic oscillator is thus independent of time, as expected for motion under any conservative force. For any conservative force, the total energy is not dependent on time. So is true for the total energy in simple harmonic motion. Now let us plot the graph of total energy with time. So the graph will very clearly show that the total energy is not changing with time. So how do we plot the total energy with time? Let us do one thing. Instead of calculating, in fact, there is no need of calculating. Let us suppose, as always, we take time as along x-axis. This is t by 4, this is t by 2, this is 3t by 4, and this is t. Similarly, let us say that this value represents half k a squared. So along this axis, we have total energy. Now, according to the expression of total energy, value of total energy is always half k a squared. That means at time t is equal to 0, t by 4, t by 2, 3t by 4, and t. Always it is half k a squared. So the expected graph would be something like this from the expression of total energy. Now we can also conclude the same result from the graphs of kinetic and potential energy. If you remember, how was the graph for kinetic energy? The graph for kinetic energy was somewhat like this. So this was how the graph of kinetic energy looked like. And how was the graph of potential energy? So let us mark it as kinetic energy. And what about potential energy? The graph of potential energy looked somewhat like this. Right? So if you see, even graphically, for both, if you combine or if you superpose both the curves, you will receive this line, which will represent the total energy. So this represents total energy, this was kinetic energy, and this is potential energy. Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.